This is a lesson on the simple pendulum in the unit on simple harmonic motion. The simple pendulum is very precisely defined as a mass on the end of a long string or wire. That's what it is. There's only a few variables involved. There's definitely a mass, some sort of mass, and what we're going to assume is that it's some sort of point mass, that the dimensions of this object does not contribute significantly to the periodic motion. The other thing we're going to have is this length here of the string or wire, whatever it is. Without going into the derivation from Newton's second law in rotation with torque and angular acceleration, I'm going to say that the angular frequency of a pendulum moving back and forth on a string or a wire is given by the root G over L. This is a mass suspended by a wire that undergoes simple harmonic motion for amplitudes less than about 15 degrees. So this is what we call small theta. Okay, small theta, so that this angle is not very large. If it gets too large, it will not exhibit simple harmonic motion. So we're going to keep it small enough that it will exhibit simple harmonic motion. The archetypical example of this is a grandfather clock. It just swings back and forth and back and forth. And you can imagine in the grandfather clock that doesn't swing very far. That angle is small. It depends on the value of gravity. G is in there, and the length of the wire. And what I'm going to really highlight here is not the mass. The mass does not depend here. Okay, does not depend on the amplitude either. Not the amplitude. It does not depend on theta, right? I said for small theta, but it doesn't matter what that angle is that it goes back and forth consistently to. So this is a pretty straightforward equation. I picked a pretty straightforward example to give us some idea of how to use it in a problem and recognize the concepts and symbols. A distant planet. Astronauts on a distant planet set up a simple pendulum of length 1.2 meters. The pendulum executes simple harmonic motion and makes 100 complete cycles in 280 seconds. What is the magnitude of the acceleration due to gravity on the planet? And this might be something we could do in lab, is verify that we have 9.8 at our region. We just put a string into a ceiling and attach a mass on the end and oscillate it back and forth, and we can count the number of cycles that it completes in a certain amount of seconds. Okay, so we have a time period. T is 280 seconds. And we have a number of cycles equals 100 cycles. And so when I think about omega, or the frequency, I can find the frequency from this. The frequency will be the number of cycles, 100 cycles, over 280 seconds. So I'm just going to leave it like that for now and say, well, I have frequency. I'm trying to find gravity. What's the acceleration due to gravity on the planet? So I'm going to solve this equation for gravity. I'm going to have to square both sides and then move L. So I get the gravity on the planet is omega squared times L. I can plug in what I know about omega for simple harmonic motion. Omega will be 2 pi times the frequency. I will have to square that whole term and multiply by the length. So I'm going to put in what I know, 2 pi. The frequency is 10 over 28. I'm just leaving it like that for now. And the length is 1.2. When I run this through the calculator, I get the gravity of the planet is 6.0426 meters per second squared, which is less than planet Earth, right? Planet Earth is 9.8 meters per second squared. And so I can only assume that it's a smaller planet, maybe acceleration due to gravity.